Hello everybody. In the last few lectures, we got into the basics of why band structures arise. We talked about the nuts and bolts of the creation of the band structure. We talked about the nearly free electron model, the tight binding model, and then we also talked about how Wigner and Seitz handled the sodium solid problem. Today we are going to explore several elemental solids across the periodic table, and we are going to ask the question as to what we expect the band structure of these solids are going to look like. And we are also going to ask the question as to why some solids occur as metals whereas others display insulator behavior. And we are also going to try to understand certain interesting trends in properties that we see across the periodic table for several solids. For a moment, let us recap what we arrived at the end of our nearly free electron picture as well as the end of the tight binding model. We essentially got bands with gaps between bands, and we also argued that certain bands have certain character. For example, the lowest band would have a S character, and then the next band would have a P-type character, and so forth. Let us recap that using a very simple picture. So here is our simple picture for a 1D solid, and of course the blue lines are our bands. The bottom one is has a largely S character, and the second one just above that has largely P character. And this is what we argued at the end of especially the tight binding lecture. And of course, the bands stop at the Brillouin zone boundary. So these are our Brillouin zone boundaries for a one-dimensional lattice with lattice parameter A. This value here is pi over A, and this value here is minus pi over A. Let us now consider alkali metals, right? Metals like lithium, sodium, potassium, and so forth. We know that in these solids, each atom contributes one s electron. What does this mean in terms of our band structure? This actually implies that our S band will be half full, right? So bear in mind that if you have a total of n atoms in our system, where n is of course a very large number, we will have n points in our first Brillouin zone. There will be n distinct points in this region over here. This essentially means that our band over here will contain a total of n distinct energy levels, right? Now, since each of our atoms is contributing one s electron to the entire system, we will have a total of n electrons that we need to place in this band which contains n distinct energy levels. Now, bear in mind that we can have 2 electrons per energy level, and so the n electrons can be placed in half of the available energy levels of this band, which is why we say that the S band is going to be half full. We can thus conclude that our solids which are made out of alkali elements like lithium, sodium, potassium, etc. Will have to be metals, simply because our S band is partially filled. Okay, so now let us apply the same logic and see what we get when we consider other elemental solids such as the alkaline earth and the transition metal solids. So the elemental solids such as beryllium, magnesium, calcium, etc. Are the alkaline earth systems. These are systems which occupy the second column of the periodic table, and they have a valency of 2, meaning that each atom in such solids would contribute 2 s electrons to the overall pool of electrons. So now we have let's say n atoms in our system, where n is of course again very large. and if each atom is contributing 2 s electrons, we have a total of 2n electrons that we need to occupy in our band, which contains n distinct energy levels, and of course each energy level can take on 2 electrons. Then we come to the conclusion that this s band is completely filled, and at that point we completely run out of electrons, and so we have a unfilled p band, a fully filled s band, and a gap between the two, and so these systems will have to be insulators. But we know that that is not the case. These are all metals, and the reason they are metals is because our s and the p bands actually overlap. We will momentarily talk about the circumstances under which these bands will overlap or can overlap. Essentially, we need to abandon our one-dimensional picture and start looking at multiple dimensions, at least 2 dimensions, to have an insight as to why the S and P bands could possibly overlap. But anyway, we will get to that shortly. Before we do that, let me also make the comment that in the case of other elements, such as the transition metal elements, such as copper, gold, silver, and so forth, the overlap between S and D bands result in partially filled bands and hence metallicity. In any case, both in the case of the alkaline earth solids as well as transition metal solids, the overlap between different types of bands will lead to partially filled bands and hence metallic behavior. Before we try to address the circumstances that could lead to overlap of bands, let us very briefly pause and revisit this topic of density of states. I say revisit because we have already encountered this once before when we discussed phonons. So the density of states is essentially a measure of the number of states per unit volume in an energy range E and E plus dE. In the case of phonon density of states, we defined it as the number of states per unit volume in a frequency range omega to omega plus d omega. Here we just replace omega by the energy, and we get an analogous definition for the density of states. So there is our definition. G of E dE is defined as the number of states, electron states in this case, per unit volume in this energy range E to E plus dE. In the case of free electrons, we know what our energy should be. It's essentially h bar squared k squared over 2m. So we start off with that, and we follow a logic that is identical to what we did when we discussed phonons. We consider volume in k-space. We consider the volume of the k-space sphere with radius k, which would of course be 4/3 pi k cube. And we ask the question as to what the volume of a spherical shell of thickness dk and radius k would be, and that is nothing but 4 pi k squared dk. So let me give myself a little room over here. So the next step is of course finding the number of allowed k points within this spherical shell, right? That we can do very simply because we know the volume of the spherical shell, which is 4 pi k squared dk, and we know the spacing between the k points. Along each dimension the spacing is 2 pi over L. So the volume per k point is 2 pi over L the whole cube. So using these two simple ideas, we can determine the number of allowed k points within our spherical shell. So there we have it. Bear in mind, of course, that L, capital L, is our lattice parameter along any given direction. We're assuming a cubic grid. And L cube is, of course, the volume V, which is essentially what we have over here. Right? So V is the volume. So the number of k points or electron states, bear in mind, within this spherical shell of thickness dk and radius k is given by this expression over here, 4 pi k squared dk divided by 2 pi cube times the volume V of our system. Thus, the number of states, number of electron states per unit volume V can be very easily written down. And let us now try to relate our energy E and K. We start off with our free electron result, E equals h bar squared k squared over 2m, and find the first derivative with respect to K, and we go from there. And so what we do now is essentially take this expression over here, consider this expression, we write down dk in terms of the rest of the quantities and stick that in here. So now we would have traded dk for de in this expression over here. We will still have k sticking out there, and we replace that k with e using this expression, and then in the end we will get the number of states per unit volume entirely in terms of E and dE. So there we have it. That is our final expression for G of E. We had to do a few elementary algebraic manipulations, and in the end we get the density of states purely as a function of E, and of course other constants, m, h bar, pi, and so forth. So the density of states G of E in 3D for a free electron gas is going to be proportional to the square root of the energy. And of course, one other point I should make here is that you see a 4 over here, and then but you see a 2 here, and that is because we have multiplied this expression by 2 in order to account for the fact that you can potentially place 2 electrons in each state. In any case, so this is our final expression. The point here to note is that the density of states is going to be proportional to the square root of the energy. This, of course, is the result for our free electron gas, and let's now ask the question as to what happens when we consider a real situation where you have electrons inhabiting a region with non-zero potential, or in fact periodic potential. Let us first draw the E versus K diagram and the density of states plot for our free electron first. So the plot on the left is our dispersion curve, E versus K curve. Bear in mind that for a free electron, E is of course equal to h bar squared k squared over 2m, so you get a parabolic behavior. And on the right side, what we have plotted is the density of states. So the density of states G of E is along the x-axis, and E is of course along the vertical axis. And once again we get a parabolic looking curve, and this is not a surprise, right? Because from this equation we know that the density of states is proportional to the square root of E, which means E is proportional to the square of the density of states, and so once again we get a parabolic looking curve. But this is for a free electron, right? So now we go back to our first curve, the curve on the left over here, and we now make the adjustment, make the modification that would ensue when our free electron is not free anymore. It is trapped in a periodic potential. So good. So there we have it. We have our blue curves now, which correspond to the situation when we have a periodic potential. Our electron is inhabiting a region of a periodic potential, and so a gap opens up. We have been through this before. Now the question is, how is our density of states going to look like? Of course, note that there are no states in the gap, and so the density of states for that range of energies will have to be equal to 0. But what about this piece over here and that piece over there? Let's take a look. So here is how our density of states is going to look, as pictured on the right side over here. So what's going on here is that as long as we are far enough away from this gap region where the deviation from the free electron result occurs, our density of states is going to track the dashed black curve, right? So it's going to be close to that. The moment as we get close to the gap, things start behaving different, and then we go to zero. Density of states goes to zero, and in the gap region, of course, the density of states is zero, as it should be. And of course, when we get to this part of our band structure, although we have done the zone folding, you have to bear in mind that this kind of tracks close to the parabolic behavior, and so we once again get close to the dashed black line with respect to the density of states. And as you get close to this part over here, bear in mind that if we were to draw our bands up top as well, we will have a gap over here, and so there has to be a deviation from the dashed black line, and then once again we go to zero. Of course, ignore this curve over here. I don't know what happened. It's a glitch in this software, I suppose. In any case, so this is going to be the density of states picture for our real electron inhabiting a periodic potential. So what if this band over here is half full, right? So let's say this band is half full and this is the Fermi energy. If that was the Fermi energy, then that is the Fermi energy for this plot, and all the states below here are occupied. And here is a little tidbit. The value of the density of states at the Fermi energy is a good indicator of the conductivity of the metal. I should say electrical conductivity, of course, right? So this so this is our Fermi energy, and so the value of the density of states at the Fermi energy, which is this quantity over here, that's G at EF, and that value actually determines the electrical conductivity. So larger that value, greater you can expect the conductivity of that particular metal to be. And of course, this is a metal, right? Because you have a band that is partially occupied, meaning there are states above which could potentially be occupied, but it's just not occupied at that particular temperature for zero field. So, so this is the occupied part, and that's the unoccupied part, but they could potentially be occupied. So this is the scenario if our band was partially occupied, and this is also the scenario when we have two bands, two distinct bands. Let's say this is the S band and that's the P band, and they are not overlapping with each other. So we have two density of states peaks that do not really overlap with each other. So now the question is, what happens when we have our two bands overlapping? How is our density of states going to look like? Let's consider that scenario. So here is an example plot where I have two bands. In fact, I've plotted just the density of states as a function of energy. So you have the density of states corresponding to the bottom band and the density of states corresponding to the top band, and they're overlapping over there, right? So if they're overlapping like that, of course you add up the density of states contributions from the two different bands, and you plot the sum total, which will look something like this. And the blue line basically represents the sum total of the density of states due to both the bands, and this little bump here, peak here, represents the fact that you have added up the density of states contributions at this intersection point. In any case, you could still continue calling this as your S band, and this is the density of states due to the P band and so forth, but the point is that they are all mixed up, especially in this region. Well, what if you had a D band, right? It turns out that D bands tend to be roughly flat, unlike the S band, which tends to be very diffuse. So if you looked at the density of states corresponding to a S band, they would be kind of broad like that, right? You know, it spans a large energy range. Whereas a D band, on the other hand, will be very sharp. It will span a very small energy range. And here is how the density of states plot would look when you have a S band and a D band overlapping it. Okay, so there you have it, the case for 4S and 3D bands overlapping. You can see that the S band generally spans a large energy range, and the D bands generally span a very narrow energy range. And so, of course, it doesn't really make sense to call this as a S band and this is D band, simply because in this energy range you can see that everything is mixed up. If you pick out an energy level in that range, you will see that the wave function corresponding to that energy level is really a mixture of D and S. And of course, as you get further and further away from the D band, you will recover more and more of the S character. But still, the right way to say it is that your wave function is really a hybridized form of the S and the D bands in this particular case. Now, let us go back to our SNP situation over here, and let us ask the question as to whether we can understand using a simple construct as to why we expect the SNP bands to overlap at all. Is there a simple way to understand this scenario? It turns out that, as I had alluded to at the very beginning of this lecture, if we are willing to go from 1D to higher dimensions, 2D for example, we will be able to see why these bands could potentially overlap quite easily. Let's take a peek. So in 2D, let us assume that we have a square lattice in real space, and so we will have a square lattice in reciprocal space, which will lead us to a square first Bravon zone. So that's a first Bravon zone in 2D, which spans minus pi over a to plus pi over a along the x-axis, kx axis, and likewise minus pi over a to plus pi over a along the ky axis. So we have a square Brillouin zone. And of course, since this is 2D, this direction here, this direction could be labeled using a pair of Miller indices, right? So this direction here would be 1, 0, and this direction here would be 1, 1. Now, the band structure for this scenario has to be plotted in 3D, right? Because our energy E is not just a function of kx. So our energy E is a function of kx and ky. So you got kx, ky, and then two axes, and then you have a third axis which is the energy axis. So E should be plotted as a function of kx and ky in 3D. But that's going to be cumbersome. So what we will do is we would plot our E along special directions, right? We would plot our E along kx first, and then take a look at that, and then we would plot E as a function of this direction, the 1, 1 direction, and we can take a look at that. Bear in mind, of course, that E as a function of ky will be identical to E as a function of kx because of symmetry. The two distinct directions would be along kx, the 1, 0 direction, and E along the 1, 1 direction. So let's now first take a look at what E is going to look when we plotted it along this direction. Okay, so there we have it. So E as a function of the k vector along the 1, 0 direction. Basically, this is kx. And of course, the Bravon zone boundary along the kx direction is pi over a. So we've got pi over a here. This is our first band, which we are calling as our S band. And then, of course, there is a gap, and then we have the P band. Of course, we did not do the zone folding here because I just wanted to avoid a little clutter, right? So really, this band should go like that, but but I did not do the zone folding. I'm just keeping it over there just for now. Okay, so you got your S band, and there is a gap at the Bravon zone boundary, which is at pi over a, and then you got your P band. Now let us ask the question as to how our band structure, our E, is going to look as a function of k along this direction, right? So now what we're going to do is that we're going to plot that curve on the left half, right, on this side. So we're going to say that this axis now is really the k along the 1, 1 direction. So there it is. So this is our E versus k along the 1, 1 direction. Now, the important point to note is that the Bravon zone boundary along this direction is over there, and the magnitude of the k vector along this direction is square root of 2 times pi over a. So this is pi over a, this is pi over a. So this point over here is at a distance of square root of 2 pi over a from our origin. So, which is why we have square root of 2 pi over a, which is of course square root of 2 times this boundary over here, right? So it's at a longer distance from the origin than this point. And along that direction, of course, we expect our E versus K diagram to curve to look like that, and that's our boundary, and then there is going to be a gap and so forth. Now, because our E has traversed a longer distance, of course, this point here, this energy value over here is going to be higher than this energy value over there, and in general, it could actually be even higher than that. And so you see why there could be an overlap. So this is still the S band along this direction, right? This is the S band along this direction. Um, and you see that this energy value over here could potentially be higher than that. It's certainly higher than that, but it could potentially be even higher than that, which means that our S band, this is still our S band is in an energy range that is occupied by our P band over there. So our S and P bands have overlapped. And this type of overlap could lead to density of states plots such as this. So you see there's an overlap there. Now you can see why a divalent alkaline earth element like beryllium, magnesium, calcium, etc. Could potentially be metals. In fact, they are metals. Well, if it was a monovalent element like lithium, sodium, potassium, etc., this band here is going to be partially occupied, in fact, half occupied, making them metals naturally. In the case of the alkaline earth elements like beryllium, magnesium, calcium, and so forth, each atom is contributing 2 electrons to the sea of electrons, and when you occupy our density of states with those 2 electrons per atom, you will see that your Fermi level falls somewhere over there, right? And there is no gap because of this overlap between S and P orbitals, and so those elemental solids are also metals. Okay, with all of these insights, let us now take a look at the situation with transition metals. In fact, we are going to take a look at this picture over here. So that's the density of states when we have S and D bands overlapping, and that is a relevant situation in the case of transition metals, which have partially filled D shells, right? And in fact, from previous discussions, we know that the bottom part of our band is dominated by bonding combination of orbitals, and the top part is dominated by anti-bonding combinations. In fact, the bottommost energy level in a band is the completely bonding combination through and through of all of the atomic orbitals that make up our wave function. And likewise, the topmost part of our band, the topmost energy level, is a result of anti-bonding combination, and everything in between is intermediate. We in fact talked about all of this in a couple of lectures in the past by taking into consideration the nodal structure of the wave functions, and we also noted that the k vector, the k index, is essentially a bookkeeping device that keeps track of all of our wave functions, and you can also look upon it as though k is keeping track of the nodal patterns of our wave function. And again, here is another nice little tidbit. When we look at band structures, we are talking about E versus K diagrams. The density of states is essentially E versus the density of states. So the K information is actually integrated out in the density of states in a picture, right? So you have your G of E in the x-axis instead of K that you're usually used to seeing in a band structure plot. All the K information has been collapsed, and it's all contained in the density of states. So this plot essentially tells you how many states you can expect at a particular value of energy. How many meaning how many, including all different values of k, because in 3D you're going to have a three-dimensional k. In any case, let's get back to our discussion. Let's focus now on this particular plot with an eye on transition metals. Right? Again, this part of our band structure is going to be dominated by bonding combinations. This by anti-bonding combinations. Starting from bonding, totally bonding, to slightly less and less bonding, and here by the time we get to this point it's kind of non-bonding, and then we are going to pick up more and more anti-bonding character, and when we get to the very top of the band we are going to have a completely anti-bonding situation. Okay, so what, right? So that's a natural question that arises. Now here is the implication of what we have just discussed. Now, because we need to start filling our band from the bottom, right? As we go from left to right of the periodic table, let's say we are going through the transition metal series, the 3D series, the 4D series, and the 5D series. Although I've said 3D over here, the same picture applies to the 3D series of transition metals, but also to the 4D and the 5D, right? So as we go from left to right of the periodic table, we are encountering systems with increasing number of electrons. And so these bands will get progressively more and more full as we go from left to right of the periodic table. Which means that when we are at the leftmost part of the periodic table, only the bottommost part of this picture, this band, is going to be filled. And as we go towards the middle of the periodic table, we are going to fill more and more. We are going to fill more and more of this band, and which means that we are going to make the system more and more stable, because we are going to have more and more bonding orbitals that are being populated with electrons. And of course, we'll reach an optimum point somewhere in the middle, right? Middle of this band, and that would be a point when we are at the middle of the transition metal part of the periodic table. And as we keep going to the right of the periodic table, we keep filling further and further. And bear in mind now that we are entering the anti-bonding regime. So as you go further and further and all the way up to the top, of course this part is filled by electrons in the bonding orbitals, but that effect is nullified by filling up of all of these other higher lying anti-bonding orbitals. And so what we expect in terms of stability is that the elements in the left part of the periodic table in the transition metal series would be less stable, and as you get to the central part of the periodic table, they would be more stable, and as you get to the right part of the periodic table, once again the stability will drop. So you will see a very beautiful pattern in the stability of those elemental solids. The way to characterize, the way to quantify the stability is using this quantity called the cohesive energy, which again we have encountered in the past. So if we plotted the cohesive energy as a function of the elements of the periodic table across the transition metal series from left to right, we should see an interesting pattern. Let's make a plot of that type. Okay, so there it is. This is a very interesting plot. What is plotted here is really the cohesive energy, which is a measure of stability of the solid as a function of the various elements of the periodic table, across the row as you go from left to right. That's what is plotted over here. So these are various elements of the periodic table. This is just a schematic plot. Bear in mind that the cohesive energy is nothing but the energy you need to supply to a solid to basically atomize it. Right? So that's a measure of the stability of the solid. So as I had indicated earlier, as you go from left to right of the periodic table for the three different transition metal series, right, 3D, 4D, and 5D, you get this kind of a result. You start from low stability, and as you get to the middle part of the periodic table, you have a high stability, and then of course as you start filling the anti-bonding levels, you start dropping in stability as well. So this is a very general trend. You see it for the 5D series. You see it for the 4D series, and you see it for the 3D series as well. Although there is an interesting deviation in this pattern with the 3D series somewhere in the middle part of the periodic table. I'm going to pause for a moment and ask you as to whether you have an idea as to why the middle part of the 3D series is deviating from the general behavior. Well, the reason is that you are encountering magnetic elements over there. So that part of the periodic table really is dominated, is occupied, I should say, by the magnetic elements, iron, cobalt, nickel, chromium, manganese, and so forth. Iron, cobalt, and nickel are ferromagnetic. Chromium and manganese are anti-ferromagnetic, meaning that electron spin has to necessarily be taken into account in order for us to get a good understanding of this set of systems. Okay, you may recall that in the past when we dealt with molecular systems, we talked about this thing called the 3S rule, right? Shorter bonds are stronger and stiffer. In fact, strength, stiffness, and the shortness of the bonds go hand in hand. So now we have talked about the strength, right? Cohesive energy is a measure of the stability of these solids. In other words, it's also a measure of the strength of the bonds. So what about the size of the bonds, and what about the stiffness of the bonds? The size of the bonds can be considered by looking at the lattice parameter, or the atomic volume, the volume occupied per atom in the solid, right? And likewise, the stiffness can be measured by using the bulk modulus, right? So what would we see if we plotted the atomic volume, or the lattice parameter, as a function of the elements across the row of the periodic table, and what would we see if we plotted the bulk modulus likewise? Okay, so our slide just got a little busier, but it's not very difficult to understand what's going on over here. First of all, what is plotted here is just the atomic volume, or you can also look upon it as a lattice parameter, as a function of the elements across the rows of the periodic table for the 3D, 4D, and the 5D transition metal series. So you can see that whenever an element is very stable, very strong, bonds are strong, the bonds are short as well. And likewise, this plot over here is a plot of the bulk modulus as a function of the elements across the periodic table, 3D, 4D, and 5D series. And once again, you can see that when a bond is very strong and very short, it is also very stiff, meaning the bulk modulus is very high. So the correlation is quite incredible and beautiful. And in the bulk modulus, again, with the 3D series, you see a disruption of the general trend. And as I noted earlier, these disruptions in the general overall trend is because of magnetic effects that need to be adequately incorporated in order for us to come up with a better complete picture. So chromium, manganese are antiferromagnetic, iron, cobalt, nickel are ferromagnetic, and these are the elements that populate that part of the 3D series of the periodic table. So we have recovered a familiar result that stronger bonds are shorter and stiffer, which we called as the 3S rule. And let me just write this down. Okay, so far in this discussion, we have largely focused on metals. What about insulators and semiconductors? What about the band gaps that we see in such systems? Well, let us very briefly look into that. One important thing that we want to note is that in the case of most metals, in fact, all the metals that we have considered so far, we have one atom per primitive cell, right? Which actually simplifies things a lot. In the case of classic semiconductors and insulators, elemental ones at that, such as carbon, silicon, germanium, and so forth, we have to bear in mind that we have two atoms per basis, meaning we have two atoms within a primitive cell, right? So this is a point we want to keep in mind. So if one atom comes with an s orbital, we have to bear in mind that there are two such atoms within our unit cell. So there are two s orbitals that come from a single unit cell. So how do we handle that? So the two orbitals can be looked upon as coming together to form bonding and antibonding combinations. And so we now keep track of the bonding and the antibonding combinations coming from each unit cell. To see all of this, let's start over with our familiar 1D lattice with lattice parameter A and one atom per unit cell. And let's picture the band structure for that familiar system. Okay, so there it is. This is something we know quite well. Now, let us consider a situation when our lattice parameter is 2A and we have two atoms per unit cell. Something like this. So that's the same system, but this time we have defined it in terms of a unit cell containing two atoms, and the lattice parameter is 2A. This situation, this scenario too, should be familiar to us, as we encountered this when we discussed phonons. The reason we want to redefine our system in terms of two atoms per unit cell is because we want to try to understand what's going on with an insulator like carbon in the diamond form, or a semiconductor like silicon or germanium. In all these three cases, we have two atoms per unit cell, right? So, okay. So when we now redefine our system in terms of a unit cell with a lattice parameter of 2A, with two atoms per unit cell, we know what to do. What happens is something called zone folding. Okay, now under this zone folded situation, we get the red curves as our new bands. Note that when our lattice parameter is 2A, our Brillouin zone will extend from minus pi over 2A to plus pi over 2A, right? The size of our Brillouin zone has halved. And because now the boundaries of a Brillouin zone are these 2 points over here, this piece has been folded over to there, this piece has been translated over to here, and likewise this has moved there, and that has moved here, and we get our red lines as our new bands, and that's our new band structure for our system with lattice parameter of 2A. So I've very carefully erased out most of the blue lines, so we are left with mainly just the red lines, the red bands, and that's kind of what we are going to focus on going forward. Let us now ask the question as to what these bands mean physically. In other words, how do our atomic orbitals combine together to create the wave functions of the entire solid? Since we have two atoms per unit cell, we need to consider combinations of the atomic orbitals that come from each atom within the unit cell. Let us assume for the moment that each atom is contributing a s and a p orbital. Right? So this atom is contributing a s and p orbital, and this one is contributing a s and p orbital. So each atom is contributing two orbitals. What happens in the case of elemental systems, elemental solids like carbon, silicon, germanium, is that the atomic orbitals from each atom go through this process called hybridization. So the s and the p orbitals actually mix up with each other, creating hybrid orbitals, right? So if you have an atom that is contributing two orbitals, one s and one p, the s and p combine in a linear fashion to create two hybridized orbitals. So two atomic orbitals lead to two hybridized orbitals. Now each of these two hybridized orbitals now combine in a bonding and anti-bonding fashion with the hybridized orbitals of the second atom. So remember, you have two atoms. Each atom provides a s and a p orbital, and the two atomic orbitals from each atom is combining in a hybridized form to create two hybrids. Likewise, this is creating leading to two hybrids, two hybrid orbitals, and the two hybrid orbitals from the two atoms now combine in a bonding and anti-bonding fashion. Those four orbitals now are what come from each individual unit cell. So here is what I've just tried to say, right? So let's recap one more time. So we have two atoms per unit cell with lattice parameter 2a. Each atom is going to contribute a s and a p orbital. That's the one from the second atom. And hybridization basically means mixing. And mixing is something we have seen in the past when we talked about metals even, right? So these two orbitals will mix together and we get two hybrid orbitals, which is just a linear combination of these two orbitals. So this set will lead to two hybrids, and likewise these two will lead to two hybrids. So we got two hybrids from each atom. Now the first hybrid from this can combine in a bonding and anti-bonding fashion with the first hybrid from that one, and likewise the second hybrid. And so the in the end we end up with four bonding and anti-bonding combinations from the atomic orbitals of the two atoms. These four bonding and anti-bonding combinations are what are going to lead to the four bands that you see over here: band 1, band 2, band 3, and band 4. So you could actually view these two bands, this entire manifold has to be composed of two bands, and those two bands are from the two bonding combinations, two out of these four bonding combinations. And these two bands in the upper manifold are the result of the two out of these four anti-bonding combinations. And of course there is a gap. Okay, so let us make this a little more realistic. In three-dimensional space, we will not have just one p orbital, but we'll have three of those, right? Px, py, and pz. So really, each atom is contributing not just two atomic orbitals, but four, in the case of carbon, silicon, and germanium. So s, px, py, pz from atom 1, and likewise those same four atomic orbitals from atom 2. So there it is. I have made my modification over here, right? Px, py, pz, px, py, pz there, and bear in mind, of course, that all of this is for our elemental solids: carbon, silicon, and germanium. Now, of course, since we now have four atomic orbitals, we need to change these numbers, right? These 2's will become 4, and this 4, of course, will become 8. Which basically means that we don't have just 4 bands over here, but we should really be having 8 bands. In fact, if you were to take a peek at a real band structure corresponding to carbon or silicon or germanium, you will see that there are actually 4 bands in this manifold instead of just the 2 I've drawn over here. 2 for 1D, but if you do it in 3D, you should really have four lines over there, 4 bands in that manifold, and likewise you will have 4 bands in this manifold. If you look at a real band structure carefully, you will see that there is actually 1 band here, and there are like 3 bands. There are 3 bands up here. At the gamma point, the 3 bands actually come together and they are degenerate, but along different directions. In the first Bravon zone, you will see splitting, and along certain directions you will see 3 distinct lines, 3 corresponding to the 3 distinct bands. So the bottom line, the point is that you will have 4 bands in this manifold, which is basically coming from these 4 atomic orbitals at the end of the day, and likewise there are going to be 4 bands up here. Okay, going from 1D to 3D really doubled up our bands. Now let us go back and take a look at the number of electrons that we have. Um, since our carbon, silicon and germanium atoms have a valency of 4, each atom is going to contribute 4 electrons, which means our unit cell, since it has 2 atoms, will have a total of 8 electrons. Right? So we need to occupy 8 electrons in this band structure over here. Right? We have 4 bands and we have 8 electrons, so all of these bands will be completely full, and we will run out of electrons at that point, which basically means that these 4 bands will be completely empty. Right? These bands are completely full, these bands are completely empty, and we have a band gap over there, which is what makes these 3 elemental solids insulators. Right? Carbon, silicon and germanium are insulators, although it is conventionally stated that silicon and germanium are semiconductors. The reason for that is simply that the value of this band gap in the case of silicon and germanium is of the order of about an electron volt. The band gap of carbon in diamond form, this gap over here, is of the order of 6 electron volts, making carbon in the diamond form a very good insulator indeed. Now, in order to round things up, let us introduce a nomenclature, which of course we are all quite familiar with, and that is that this manifold here is essentially called the valence band, and this manifold here is called the conduction band, with of course the valence band being fully occupied and the conduction band being fully unoccupied at low temperatures and in the absence of electric fields. Now, this entire discussion has provided us with a satisfactory qualitative description of the electronic structure of a variety of elemental solids made out of elements across the periodic table. Now, let us take a very quick glimpse at the periodic table itself to get an idea of the amount of terrain that we have covered in this discussion. So here is our periodic table, and in today's discussion we talked about solids made out of the alkali elements which are sitting over here. We also talked about solids made out of the alkaline earth elements which are over here. And we then moved on to considering transition metal solids in the 3D, 4D and the 5D series, which are right here. And then finally we ended up with elemental solids made out of carbon, silicon and germanium, the classic insulators and semiconductors. What we did not touch are the big atoms such as these, and we also have not yet talked about semiconductors that can be built from elements from this column and that column of the periodic table. In previous lectures, we considered the molecules made out of these elements, as well as molecules made out of these elements. The point I wish to make is that modern band theory or electronic structure theory, which has evolved over the last 100 years or so, has become enormously successful in explaining the behaviors and the properties of a wide variety of molecules and solids made out of a good part of the periodic table. So this is all very exciting indeed. Thank you very much.